like this?
Yes. Yeah. We can say
Okay,
it.
so what I understand from Dr. Anand's briefing is that I get 20 minutes to present and then it will be more open question answer round.
Yes.
Yeah, okay, so I'll start if
Yes.
is there an echo? No, okay. So, hi everyone. Today I wanted to talk to you broadly about the work that I do in hydrology and water resources. I am an associate professor at the Department of Civil Engineering, and I'm also affiliated with the Center for Climate Studies at IIT Bombay. I have listed my email and contact webpage for you to know more about my research. Um, Broadly, what I do has two, three foci. So first is I've been trained as a hydrologic modeler. So my PhD was in rainfall runoff models and their improvement under changing climate, and also in predictions in poorly gauged basins. So although my portfolio has evolved since my PhD, I still do some work in this area. And now, majority of the research I do focuses on some components of thinking about how humans are affecting hydrology or how we manage water. So reservoir operations is a big part of what I do now. But beyond that, I've started doing some work also on developing models of coupled human water systems. And also, whenever I get an interesting problem in terms of understanding human influence on hydrological fluxes. So I try to work on that too. Now, I've been post PhD. It's been around 10 to 11 years for me. So now I can look back and think, what have I done, right? So when you're initially in your early stages of your work, you very focused on specific aspects. But after a while, it's good to look back and see whether you've been doing what you wanted to do. So this is the pastures quadrant that Stokes came up with in 1977 to help us classify where our science, our research fits. So on the x-axis, we have applications to the society. So we may have no immediate use for society right away, or we may have actionable science. And on the y-axis, we have knowledge generation. So when you're doing pure research on the top left, you are answering questions which are more for the understanding of the phenomena, but you may not directly see their use in terms of management or policy making. And whereas when you are on the top right side, you are doing research which is directly linked to some policy relevant questions. So use inspired fundamental research. And the bottom right is pure applied research, where you have questions which are very actionable in nature, but they may not have a lot of science component in them. A lot of reservoir operation literature is sort of between the two, quadrants on the right side, because we know a lot of the physics which is involved, but at the same time it is challenging. So the analysis and understanding is more on how to, properly convey the information we have. And the bottom left quadrant is often left empty, but I think sometimes we do work which is purely from a communication perspective, letting people know about the type of impacts that can happen. So sometimes I have done work in that area too. So today I wanted to talk briefly about some of these. Not everything can be covered in 20 minutes, but just to give you a few, uh, you know, um, glimpses into what we've been doing. So the first question that I think falls into the pure research category have been on how do you adjust hydrological model parameters in a changing climate. So a significant body of hydrology literature has been focused on assessing the impact of climate change on river runoff. And typically, the way we do this is we take a hydrological model and we use historically observed climate data. And maybe I'll use a pointer. And then we create stream flow simulations. And by using the observed stream flow data, we fit this model. When we fit it, we get model structures and model parameters that are representative of a region. And then in order to predict future hydrological fluxes like ET or soil moisture or runoff, we then use climate information into this fitted hydrological model. Uh, but when climate changes suddenly, now there is at least more than a decade worth of research that shows that this approach does not really work well, because as climate changes, the fundamental nature of catchments change and they co-evolve with the climate. So there is now work ongoing in terms of how do you now fix this, because climate is changing. We cannot use historically calibrated parameters anymore, or can we use them, under what kind of conditions can we use them? So one of the things that I've been working on was how to answer that question. So it's more of an exploratory research. So one idea in this domain was to think about broadly how different biomes of the world are classified based on climate. So we have, based on temperature and precipitation, this Whittaker's biome plot. And if we have a catchment, let us say, which is in temperate seasonal forest regime, but climate change shifts it. For example, a lot of catchments will be maybe on the border or close to the border. And if you have significant climate changes in temperature and precipitation, it's possible that it moves in another quadrant. So what we did initially, just as a way to test the hypothesis, is to take watersheds across the US which did not have any human influence, significant human influence, and categorize them into their respective biomes based on this plot, based on their historical climate, and then just calibrate them and look at the distribution of their parameters. Because if the parameters don't have a specific biome imprint, then it doesn't matter, and calibration shouldn't be affected by changing climate. But instead, what we found that the parameters of this parsimonious hydrological model, the snow parameters, the soil parameters, so these are all the parameters of the calibrated model, and the colors of the distribution functions, the cumulative distribution function for each biome. And we saw a difference, and this was what kind of proved the hypothesis that there is an impact of climate on the parameter itself. And we use this information, without going into a lot of details, to do what we call trading space for time. So once a catchment, let us say, moves into a new biome, you can use or borrow the parameters of that biome based on certain regionalization approaches. So regionalization has a long history in hydrology, but this is one of the first times that we were regionalizing in the using the space regionalized information to think about what will happen when the catchment moves in time. And we tested it with some catchments where 40 years of data is available. So on the top, you see what happens if you don't change the parameters with climate. So red is the observed and blue is what you predict. And then when you make that adjustment based on the changed biome, then you have a slightly better fit in terms of getting the peaks right, and you have a more confidence in your prediction. So this is an ongoing work where still a lot of research is can happen, because catchments have just started to show or exhibit this changed response to climate. Now moving on quickly to the other part of my work that I wanted to present today. It's on the work that I've been doing in terms of how humans impact hydrology. So in this, there are two aspects. One, you can just work on inferring the human's signal in different hydrological fluxes, and this can be done at various spatiotemporal scales. So one work that I wanted to show you today was how we have done it at the scale of the entire India. And the second is a more place-based analysis, how we think about our fundamental models and how we tweak the models now to include humans as actors in the model, just the way we include various runoff generation processes and everything. We need to now put those boxes in there, which also show how humans are altering the ET or other fluxes. So moving on to the first work in this. So here what we did is we used a model which is a very simple mapping of the water and energy balance in a catchment. It's called the Budiko model. So the Budiko model essentially plots the catchment's water balance, which is the y-axis, the ratio of the actual evaporation, evapotranspiration to total precipitation on the, and the x-axis is the ratio of the potential evapotranspiration to precipitation, and this is all on decadal time scales. So we do this kind of analysis for 30 years of record at least. And some catchments will evaporate more than runoff, other catchments will generate more runoff than evaporation, and the placement of the catchment on the Budiko curve can be governed by this omega parameter. So omega will decide how, to what extent, your precipitation which is falling on a land mass, either it will evaporate or it will become runoff. And that is a very fundamental behavior of a landscape, the way it partitions rainfall. So we took the districts of India, and instead of using ground-based data on stream flow to calculate the y-axis, y-axis is typically represented as 1 minus q by p, which is runoff ratio. But we directly took satellite data on actual evapotranspiration and calculated this ratio for different parts of India. And you can see that different parts of India fall in different regions of the Budiko curve, because they have different water and energy conditions on long time scales operating inside them. Now we took those regions. These are around 600 districts in India. Each district is a dot here, and we took each district and we calibrated this omega parameter. And in the next analysis, we took this omega, which varied across India, and tried to think about, is omega showing more of a signature of climate, or landscape properties, or human impacts, right? So we took a large database of climate, soil, vegetation, human, and topography. So various climate indices, including mean annual temperature, precipitation, seasonality index, various soil indices like clay to silt ratio, various indexes of land cover, like how much is the short rooted vegetation, how many water bodies. There is a longer list that we used, and then we used a machine learning algorithm, random forest, to identify the predictors which strongly explain the spatial variability of omega across India. So this is the final result on the right side, where you see that climate is by and large the most dominant control, even on omega. I mean, we are already using climate to explain the runoff ratio, but even to explain the omega values, climate is important, which means that primarily things are being governed by climate. Soils are the next most important controls, the type of soil and then vegetation. And humans don't show that much of an imprint in when you compare them as drivers against the other natural characteristics. But they did emerge as significant predictors in the random forest algorithm, which means they are not yet reached, at the scale of large land masses. It's still climate and soil which decides the water partitioning behavior. But when you're looking at smaller patches, population density, percentage of cultivated area, and dam capacity becomes important. So this is one way to answer the question, do humans significantly affect water partitioning behavior across a large landscape? We've been also doing work on smaller scales. For example, how do you understand groundwater level fluctuations in an urban area? And we have developed a parsimonious model of predicting groundwater head as a function of climate and pumping in the Hyderabad's metropolitan region. And there is an open source toolbox for that, which anyone can use for any region where climate and pumping information is there. You don't need exact data. You ranges, and then the model calibrates and presents different answers based on the goodness of fit for the head data. So now the second half, I wanted to move into the reservoir management, which is the work which I've been doing primarily for the last, you can say, 5-6 years. And in that, I've now started working on human water feedbacks, how they appear and how they can be used in better managing our reservoirs. So large reservoirs are very critical to ensuring water and food security across the globe. There's a lot of challenges related to them. For example, there are ecological issues. There is also the issue of managing conflicts between multiple sectors, multiple actors. Um, but they remain imperative in the functioning of our economy. And therefore, it's useful to understand how we can use them more effectively, how we can use all the hydrological data which is available to us to get better outcomes in terms of our flood protection, hydroelectricity, irrigation, and environmental flows requirements. But there are key challenges that have emerged. One is again conflict. I have already said listed it here. The second challenge in managing large reservoirs is that they have a very long lifetime. So they have to deal with the fact that you may be designing the structure based on past stream flow data, but the structure is going to work in conditions which you probably couldn't even have imagined in the future. So we call these uncertainties deep uncertainties, where we don't know exactly what will happen in 30 years in terms of rainfall or even demands. And the third aspect of that uncertainty or challenge is the human water feedbacks, that if you make a large reservoir in a region, it changes that region. And then that changes our needs from the reservoir, then we may make more reservoirs. So there is a feedback loop. And in terms of broader understanding, it is important to understand at that level these human water feedbacks. So I'll take the example of the Nagarjuna Sagar Reservoir on the Krishna River to show some the work that we did. So this is one of the earliest projects in terms of large infrastructure investments. And the way reservoir operation literature will deal with this problem is we take the inflow data and we have a reservoir water balance, which is simply just add the inflow, subtract any releases, and so on and so forth. And we use an optimization to identify, some release rule that optimizes all our goals. So there's a huge body of literature just doing that. For example, in the case of Nagarjuna, when you think about the major conflicts that emerge when just focusing on Nagarjuna Sagar Reservoir, it is between satisfaction of irrigation water requirement and hydropower generation, which is expected because in order to generate a lot of hydropower, you need to maintain the head, the storage in the reservoir. But then in that same storage is irrigation water. So if you send it away, you have less hydropower. What is the use of this type of analysis? Here we are showing you, on the right side, the trade-off between hydropower and demand deficit, the shortage of water which could be supplied for irrigation and domestic needs. And you can see that if you maximize your hydropower production at 3,900 gigawatt hour, you have 500 plus million meter cube of demand deficits and vice versa. So this kind of information can be used by the operator to think about how they want to operate and which part of this trade-off space they want to be in. We've also been looking at, minimum environmental flow if impacts from the reservoir. What we found is that if we operate the reservoir using the historical data um, and set a literature-based, threshold for environmental flows on downstream, then typical operation routine which prioritize release of water for irrigation followed by other uses will not lead to getting those environmental flows satisfied. So we've been trying to ask the question, is it possible to prioritize the releases for minimum releases for the environmental flows and then, do all the other releases, and not showing any results here. But what we found is that depending on the nature of the reservoir, you may just need to tweak the operation and you will be able to prioritize environmental flow with minimal impacts on the other objectives. So it depends on the reservoir type. So moving on to the human water demand aspect of this work. So after working on the Nagarjuna for 3-4 years, we finally decided that we should talk to the people in the command area of Nagarjuna. So Saivina, who has done this work, she went and she actually interviewed reservoir operators, environmental groups, and water users in this area. And we just wanted to see whether the type of optimization we are doing and the results we are getting have any value for the user group. What we ended up learning from them were that our systems model is not necessarily what is happening on the ground. One of the first things we learned was in these command areas of large reservoir, although you are supplying surface water, groundwater is still being used to supplement surface water. So if you want to understand water security condition of the farmers, you should be simulating that conjunctive use. So whenever reservoir water falls short, you should be having a process in your model to pump the groundwater up. We learned many other things like what are the rules of thumb sometimes reservoir authorities use in that region to fill and spill the reservoir, which was not coded in the model. So you will not be able to realistically reproduce the storage in the reservoir, which has happened in the historical time period. And we learned how farmers adapt to deficits. When they actually face deficit, they take different decisions if it's a short-term deficit and different decisions when the deficit may be of 5 years or so. And based on that, we developed what are called causal loop diagrams with and without their input. So without their input, on the left was what we thought is happening, that there is a climate component that feeds into the reservoir, and then that goes into the command area. So these three were our original mental maps, you can say. After talking to them, we added two more components. We added a groundwater component for conjunctive use simulation, and we added a demand adaptation module to adapt the farmer's demand whenever there is a deficit from the surface reservoir. Based on that, we developed three conceptual models of what might be happening in the command area of this system. And we then used available data to validate the output from these three models. So the first model is our vanilla model based on water balance. In the second model, we had the reservoirs rule of thumb included, the groundwater included, and in the third model, we added the adaptive water used by the farmers. And what we found is that the model that simulates or includes the adaptive water use and the groundwater better captures the storage which is observed in the reservoir after a multi-year drought. So there are signals from our result that when there are multi-year droughts, there are significant changes in the behavior in the system, and that water use adaptation. It's important to know how that is happening in order to correctly understand the water, food, and energy security in the region. So we validated the work, and it's still under review. The main learning that we had from this is that if you go and actually talk to the users of the water in these large command areas, you may identify certain hydrological processes that are being affected. And then that can help you better model the system and better understand in the long run what may be happening in terms of droughts or climate change. So with that, I wanted to just end on time, leaving this more of a interaction than a talk. These are the four broad questions that I think I will be working on for the next few years. Or the first one related to modeling. I don't think we have still solved the puzzle of how we update model parameters with changing climate. So we'll continue to work on that. And then there are a lot of unanswered questions on how do you quantify relative impact of human activities on hydrological fluxes across a spatiotemporal scale. So one of the study we did with the Buddhi Cook work was for an entire India scale, but there are works which do look at basin scale and urban scale. So there are so many ways in which how humans are affecting the hydrological cycle. We know they are affecting, but to what extent are they affecting? Are they becoming an important driver? Then at which scale? And the third work is going to continue on the building of human water interactions in the models. So continuing to improve our existing models to better include how humans are becoming a driver in the model by giving a feedback, especially in these reservoir operation models where humans are intrinsically involved. And basically all of this we should do with the primary motivation for me is to help better manage the water resources while also continuing to ask and answer interesting science questions. So I would leave you with that. Over to you, Dr. Anand.
Thank you, Dr. Riddhi. It was a great presentation. So I have a couple of questions on climate change, which I'm going to ask later on. But we'll start with questions from Vinay first. Vinay, do you want to go?
Shall I stop sharing my screen?
Yes, please. Yeah.
It's done.
Vinay, you're muted.
Yeah, Dr. Riddhi, I just have one question from my side. I just would like to know, what is your recommendation in choosing type of hydrological model? We see, many researchers, sometimes they go with the SWAT, mostly they go with the SWAT, they go with the WIC, they go with the WRF hydro, right, SPHY. So a lot of hydrological models are there. So what is your take on those models, and what is your recommendation, for young researchers, while they are choosing an appropriate model for their study area?
Okay. Maybe I can answer it with an analogy. I use it with my students. You know, how sharp should my knife be? Should it be an automatic cutter, or should I just use my hand? It depends on what you're going to cut, right? So it depends on what do you need. So if you need to answer questions like within catchment changing soil moisture conditions, then of course you need a distributed hydrological model because otherwise you won't get the answer. Now in my research, my questions have been um, is the output from these hydrological model reliable under a changing climate? So whatever I'm finding is going to generalize to any model. So that is why I use conceptual models which work at the entire scale of the catchment. And when you go for conceptual models, they should have all the processes in them. But I don't think there's a best one. It's just what you want in terms of what's your science question or what's your applied question. Then based on that, you choose.
Yes. A follow-up question to this. Sometimes, some models like SWAT are developed for agricultural watersheds, but we see, some researchers, they try using that in a mountainous region or for the snow-dominated catchments. So how is that impact is going to be there on the overall result in terms of the percentage change of the stream flow or whatever?
So, when you say model SWAT, essentially is just a few equations with parameters, right? And what we end up doing is we calibrate it. If you want to understand whether that model there are two questions. One, did the model fit the data, right?
Yes.
And the second question is the processes, are the processes which the model is telling realistic? And you can check this, you can check both. And now we have so much data that we don't need to
Yes.
only rely on stream flow. So you
Yes.
have groundwater data, you have ET data from other sources. So using multiple data sets to check your model performance is really, in my opinion, the first way. And the second is, let's say a model has a few components and it is saying curve number of something, right? After calibrating, you get a certain curve number value. Then you have field data and you can see whether that is realistic or not. Is it simulating the kind of base flow that is expected in that kind of hydrogeology?
Okay.
So
Uh, yeah. So sorry, one more question. I just have it because when it comes to the Jammu and Kashmir region, the catchments here are very poorly gauged. In the sense, say for example, if I go to the Jhelum Basin or the Tavi Basin or some places in the Chenab Basin, the catchments are very poorly gauged. Sometimes we don't have enough data to calibrate the models actually. So do you have any suggestion, in calibrating such kind of the models? Whether can we use some other data for calibration of such models rather than going with only stream flow based parameters?
that's what I was saying, that multi-data based calibration, there's quite a few papers now. Of course, I wrote my Buddhiko work on satellite data,
Okay.
satellite ET. So I closed the water balance from satellite ET. Now, I'm not saying satellite ET is great. It has
Yes.
its own biases. But
Mhm.
I was having a study across India. So
Okay.
in that case, depending on the resolution of your product and the averaging size of my districts, it was it was okay in terms of spatial resolution. So and then now you have other satellite based information on soil moisture, or you may even get what graze gives you, but it may not be useful for very small catchments. So very
Yes.
small catchments, there is no option but to measure. But if you've got a larger catchment, see, if you have a
Okay.
larger catchment, chances are it is monitored. Um,
Yes.
and whatever in terms of filling the gaps, you use satellite data, or maybe ground department has groundwater head information, and you
Yeah.
put it all together.
Yeah. Why I'm specific to Jammu and Kashmir, only one groundwater monitoring station in entire Kashmir division. We have only seven groundwater gauging stations in entire Jammu region, which covers 17 districts also. So it becomes sometimes very difficult for us in calibrating the hydrological models because we don't get long-term data, and because these rivers share the international boundary, we find it very difficult to get the data on ground as well. But the suggestion that you have given is like satellite-based DT estimates, that also we can look at. I think possibly we should also look in that direction. Yeah,
See,
thank you. Yeah.
the way I see it is, you're constraining the uncertainty.
Yes.
You can never get the right answer, but you
Yes.
use all the data just to constrain the response. And
Yes.
even places where we have data, look, predicting under climate change is predicting in a time when you don't have data.
True,
That's
true,
why
true,
I said that research is open ended, because
true.
even if you have 50 years of data, if a catchment
Hmm.
undergoes significant climate change, none of that information is very reliable, or yes, some
I
of it
understand.
is. but the partitioning behavior will change. So you need to go back to the fundamentals anyway. So it's the prediction under gauge in
Yes.
ungauge basin, the regionalization literature and the predicting under climate change. They have
Yes.
they can borrow from each other. Like you can see if there is a way to regionalize from other mountainous regions where there is data, right? I mean,
Yes.
of course, it may be all wrong, but it is a way of just testing theories and saying,
Yeah.
what might be a possibility.
True, true, true. Thank you, Dr. Riddhi. Anand, there are some questions in the chat box. Yeah.
Yes. Yeah. So there's a question from Rishi. He's asking about optimization curve for the reservoir. So when we look at sedimentation, does that impact the demand deficit and the power generation? Is the curve going to be stationary, or does the sedimentation impact that curve?
Yes, sedimentation of course impacts all our reservoirs. It changes the available storage. So if it is coming to the point where live storage is getting affected, because there is a dead storage and there is a live storage. So if it starts affecting the live storage, then it reduces it and then you re-optimize, of course. In our studies, at least for Nagarjuna, we did not look at that. I mean, I think it from the data we had, it was okay to do it for Nagarjuna, but you have to look at the reservoir. Some reservoirs which will have heavy influence, you probably need to account for that, changing storages as you do the optimization.
Yeah.
Yeah.
And there's another question from Prem Prakash, but I think it has been already covered on how do you choose the data when there is very little data available on groundwater or sediment data or pumping.
Uh,
I don't know. I'm assuming it's for the command
Yeah.
area. Was the um, I always get the data question in the talks, but when I have worked, I've never faced the data problem. So when I went to the authorities of the Nagarjuna Reservoir, they happily gave me all the data they had, and they said, "You're welcome to come back and show us what you got."
Mhm.
So maybe I framed problems that can be answered with the data I had. I don't know what I did.
I think the first step is to start talking to people.
Yeah.
Yeah. Yeah. So
Thank
my question is, like, what do you think of climate change predictions? Some people use hydrological models to predict flow rates in 2100 year, like 100 years from now. So what are your views on it?
Yeah. I think by now we all know that we can't predict what will happen in 2100 with any reasonable confidence. Because we don't know how the carbon dioxide concentration will vary, because we don't know if we will react to the signal. And so I think in terms of what their literature or where the science is now going, we now do what are called stochastic inflow realization. So we take observed data and then we perturb it.
Hmm.
And as I said, from the reservoir operation and the planning of infrastructure perspective, the entire decision analysis literature has moved away from relying on those predictions. So for any real decision making, you are either only looking 20, 30 years ahead when there is quite confidence in the climate model also, or you are using what are called these deep uncertainty, decision making under deep uncertainty based approaches. So robustness analysis or adaptive frameworks where you say yes, I don't know. So even if you don't know, I still need to invest X trillion dollars apparently, and so we just need a way to flush this out based on 100, but we still need to make a plan for projects that last 50, 60 years. So we have, I mean, what I've been learning is we should be doing it with much more analysis than perhaps it is being approached right now.
Mhm. Yeah.
So, Dr. Riddhi, what do you think of improvement in the hydrological models over the last 20, 25 years? Because we have seen there are many hydrological models that are coming up, right? So,
Yeah, that question I don't know. I mean, some of us are still using PDM and we are happy with it. Sometimes we add more processes. As I told you, you can add more processes if you have a way of validating the existence of the process. So in parts of the world where there is good amount of data collection, models have gotten more complex based on that information, not simply because we have more complex models. And you might be aware of the modular model building frameworks where you have multiple process components for each major hydrological process and you test everything. So, as you said, now no more in some of the literature, we don't use any single model anymore. We have for evaporation process, we may have 4 routines. For run, you think that's more representative. So in terms of the advancement, I mean, there have been advancement in process understanding, but I think in terms of model use, we still have to understand when to use our models correctly. Yeah.
And so what do you see the next 20 years is going to be in the model development? Like, or what do you like to see in the model development?
I just told you what I'll be doing for the next 10 to 15 years. A major focus for me will be to look at the, coupled human water models, because when we interviewed the farmers, we only got one, initial round. We learned so much that we changed our causal loop diagram, right? Then we learned from that analysis, post analysis, that there is a very significant impact of multi-year droughts. As soon as multi-year droughts happen, the system kind of shifts a little. And so now we are trying to do a little bit more analysis on 2 large droughts on record and how they might have affected. So I'll be working on, I will not say what everybody will be working on, but I will be working on the ways in which in these very human affected regions, how can you better improve the, in a simple way, okay, not in a very complex way, in a simple way, how we may be responding to the water system. And I think enough people have by now understood that 2100 predictions out in 2100 may not be useful. So there is also now literature on this, how do you use the existing information to still provide climate actionable, actionable things. So I'll be working on those things. Um, Apart from that, there is a lot going on in hydrology in terms of, isotope hydrology and what all. I think those things will continue to go on. My answer will remain focused on what I will be doing.
Yeah. Thank you.
And a later question from my side, how do you balance your personal life and the professional life? Because most of the times our profession demands, time in office. So how do you manage both the personal as well as the professional life?
So the key is efficiency. If you can be efficient from 9 a.m. to 4 p.m., I think you will get a lot done. The problem, I think, is our ability to partition our time and be efficient in the time. So I personally feel that I'm a very lazy person. So I don't balance a lot. um, and I also, there's another thing I have learned after I have a daughter, that it helps to not think about work for some hours of your day, because the next morning you will come with a more refreshed mind. And I mean, this is for people who do science and are stuck with a problem for months, maybe years. So they always remain in the back of your head with all the things people are doing, but you are constantly and I try to manage time. That's, I will say, that is how I try.
So actually, what interested you to study hydrology? So what made you come down this path and how did it all start?
I think I wanted something which gave a good story and a ring to it. So when I was in my bachelor's, which was in civil engineering, I I was searching what I will be doing, because I found that, whatever you do in your professional life, you will be doing for a long time, and it should give you satisfaction, not just put bread and butter on the table, because if you don't have satisfaction, then I don't know. So I explored many things before I came to hydrology, and I started doing a lot of projects, green buildings, this and that. And it so happened that I was getting more success when I was doing water related things. I was getting internships in that. And at the end, I got scholarship for a master's to study hydrology and not environmental engineering. So I never decided that I will do hydrology. I applied to both because at that time the idea was environmental engineering gives you more job security. But my heart was always in hydrology. I knew it. I mean, just from my internships and all, I'd gotten very interested. And also, when I was doing my bachelor's, in those 4 years, there was a drought and there was a flood in that city.
Okay.
And yeah, so first there was a big flood in the second year, and then by fourth year, the lake was dry and which supplied water to the city. So I was like, wow, this is interesting because you've got nature and then people are fighting. I saw that. I saw what happens when there is a hydrological extreme. So I thought, well, this has a societal angle to it. It has science in it. It has all the things that, a curious person may enjoy. So, so there were
Nice.
multiple factors, and also fate because I got the sponsorship for doing hydrology. So it's both.
Yeah. Nice.
I just would like to add, Dr. Riddhi, I think I did my master's and PhD from IIT Guwahati. So the Brahmaputra River next to IIT Guwahati campus, it gave me inspiration to work on that particular river system. Because you may be aware, there are a lot of issues that are associated with that particular river when it comes to hydro and bank erosion. So sometimes the problems around us actually makes us to work or to explore more in that particular area, also in providing some solutions. Thank you.
Exactly. Yeah. Exactly. When you that, but that means that you have to observe what's around you.
Yes, yes, yes. Sometimes, sometimes we use morphological models, we use hydrodynamic models. They could not actually predict the complex processes that actually happens in the river. I mean, unless and until you see the river, you see the processes that are happening, you cannot actually rely on the model that you are actually using it. You are not sure the model that you are using is capable of predicting such kind of complex hydrodynamic or the morphological processes. First, I believe it, looking at the river or, looking at the field, you get to know what actually the processes that happen there, and whether the availability of the models that are there, would be capable of predicting such processes. Thank you. And I just would like to add one more question to this. You may have conducted many field surveys for the research. Did you have, I mean, do you have any strange experience, while you were on the field, while collecting any data or so?
So I will now make a confession. The rivers on which I did my PhD on, the first time I visited one of them was way after I got my job as a faculty, and I was like, okay, this is how that river looks. So it is possible to do your entire PhD without going and seeing the site, especially if you're working on large data set hydrology. So I was doing comparative hydrology with multi-decadal data sets. But I used to help out my friends who were doing field work in Penn State. So we used to go to help our fellow students. So I've gone for them. And now, of course, for Nagarjuna and all, the students go. Weird field sites, nothing. It just used to rain a lot, and I used to feel for the field hydrologist. That's all. Their life is very hard.
True, I understand. Well, because I again remember, while we were conducting acoustic Doppler current profiler survey on the Brahmani River, we were on the mid of the river on the survey board. It started heavily raining, right?
Yeah.
Uh, that was very difficult situation for us to handle because we have our equipment and the turbulence inside the river increases because of the wind action, and you have your laptop which you use it for the collection of the data. So that was one of the weirdest experience for us, to manage on site, while collecting the data. Right, but because sometimes the conditions are so challenging, like, another experience I could share, when we were there in Tawang, Arunachal Pradesh, where the temperature was almost -3 or -4. We have gone there to do the cross-sectional survey of the river for setting up of the hydrodynamic model. After we have gone there, our total station batteries got drained off and it didn't work eventually. And we
Hmm.
have taken some of the velocity measuring equipment, they didn't work eventually. So finally, what we have used some traditional method, like ball distance and the time-based method for the computation of the surface velocity. So sometimes, you find it so challenging when you go to the remotest locations, or, when you land up in the, when you are on field and it starts immediately raining, that is a very difficult things to handle it.
Yeah. So in my case, the field work is more in terms of interviews and interactions and just observing, water supply conditions or some how good the crop was. So it's not exactly field hydrology,
Yes.
but it has its own challenges identifying the right people to interview and people not wanting to share information. So how do you make them comfortable when you're talking to them
I,
about this?
I completely agree to that. I completely agree to that, because when we were conducting socio-economic survey in the Kosi region, as well as in Arunachal Pradesh region, people were highly resistant to talk to us. They look you as an outsider. They may have a lot of local problems. Say, for example, if you look at the Kosi region, every year the river is flooded, and you see the embankment breachings that are happening. When you go there and when you say that, we are trying to look at your experience, what are the problems that you are facing it, these kind of the surveys, they have been participating from many people in the past, but eventually no solution is landing up for them. So it becomes so difficult for you sometimes, in the socio-economic interaction surveys, to get the required information what you are actually looking at. That's true.
Yeah, but we have to keep doing it.
Yes,
You
yes,
know,
we have to keep doing it somehow.
I
We
think
have
that
to.
disconnect creates a lot of problem in our field. So
Yes,
some,
yes, yes.
not everyone, but a portion of our field needs to be, in that
Uh,
direction.
I agree. I agree. Yeah.
And I think now we'll ask the participants if they have any questions. So please feel free to unmute and ask the questions.
Yes.
Yeah. So what is your take on AI or machine learning? Because you mentioned satellite data. Now people are going towards AI. So what do you
Hmm.
think of it?
And we see applications
Yeah,
as well. Everywhere
I
we are
think,
seeing it. Yeah.
my answer is exactly the same as the question on which model to use.
Mhm.
It's, you've got a blender, you've got a knife, you've got your own hand, so it all depends on the question. For example, if you're doing stream flow forecasting for a reservoir, AI might be your best option if you're doing real-time operations. But if you want to understand whether I need to change the policy of operating this reservoir from being a flood protection reservoir to both hydropower and flood, then of course AI will not help you.
Mhm.
So you need to use AI when you need it. Like in the case of random forest that we had a large database and we needed to search which is the most important predictor. Now there are many algorithms that can do it. You just use a reasonably good algorithm. And of course, you must have noticed this trend of coupling AI in hydrological models to fill in the gap for some of the process understanding.
Mhm.
So that is happening a lot now. Only after 5, 7 years, we will know to what extent that worked. So as I said, I mean, very good for getting high accuracy prediction. So any problem where that is of use to you, near-term high accuracy prediction, they are useful. But if you're thinking again about developing process understanding, it may not be the thing to start with. So I think one of the challenges that computers themselves have brought to hydrology is we don't spend the time to understand what the model may be doing. It becomes a pretty much of a black box, an input output. But I coded my first conceptual model line by line. And then I spent a lot of time in thinking this process, this parameter setting will lead to this, to the point where ultimately my advisor had to tell me to stop because I was not progressing at all. So eventually he said, cut it out. And but now I think, that capacity to just sit with your model and think about it for a long time, I don't see it a lot. And I think we still need it because conditions are changing, climate is changing, humans are influencing. So if you need to be ready to conceptualize these new processes, should it be a linear equation, should be a quadratic, how will I conceptualize this process? Our perceptual model of hydrology is changing. If you
Yes.
now open some of these NOAA and USGS sites, textbook hydrological cycle, which we learned in class 8 or so, now have humans in it everywhere. And so if you're gonna now make new models, you should be very comfortable with old models or existing models. So if you go the AI and all path, I think some questions just cannot even be attempted. So it depends, right? If you're doing data assimilation and improving prediction forecasting, yes, that is the best product out there. But
Yeah.
what is the question?
Yeah, sure.
Some casual questions, Dr. Riddhi. What is your favorite movie?
Oh my God, I watch so many movies. I don't have one favorite movie. I have many. I think if I had to just speak just like that, it's a English movie, Patch Adams. I don't know. I'm old.
We need to look it up.
Yeah, look it up. Look it up.
Yeah. And so is there any particular paper that has largely influenced your research or something that changed your research direction?
Yeah, there is a paper, I think, which influenced my philosophy, which I've spoken about in this 1 hour. It was the paper by Keith Bevan, Changing Ideas in Hydrology, the Case of Physically Based Models. And that paper was given to me by my advisor for my candidacy exam presentation. And here, Keith Bevan, has elaborated a lot on how useful physically based models are, because even in 1989 people thought that computers will solve everything, and the more computing resources you have, the more answers you can have. But I think that has not happened, and I hope people understand that. And Keith Bevan in 1989 wrote why that will not happen. you know so
Nice. So any last questions from you, Vinay?
I think I'm done.
Okay. So any questions from the participants? I think there are no more questions, but we really thank you for taking time out of your busy schedules and for this presentation. Really appreciate that, and hopefully we'll keep collaborating in one way or the other in the future. And I encourage the participants, if you need any clarifications or further support, I assume Dr. Riddhi would be happy to answer your questions through email. So with this, I would like to conclude this session. Yeah, thank you so much.
It was
Thank you,
very
Dr.
nice
Anand
interaction
and
with you,
Kimball.
Dr.
Thank you
Riddhi.
so much for organizing this. Bye.
Thank you.
Thank you. Thank
Bye.
you so much for joining us. Thank you.